I'll just pause and make sure that everybody can hear me. Can you hear me, Sarah?
Yes.
Okay, great. So it's really a pleasure to be here at Wayne State. I was telling Dr. Mossad that my father-in-law, I think, played collegiate baseball for Wayne State a long time ago. I'm not sure when that was, but he has fond memories of growing up in Detroit and being at Wayne State. So today I'm going to talk about what the interoperability challenges are for specifically an augmented reality capable digital thread. And that's very much a loaded title. And I hope to shed some light on each one of these individual topics. And also it's a bit confusing where I sit in Air Force Research Lab. It's a fairly large organization. So I plan to spend at least 10 minutes or so explaining how folks outside of AFRL can interact with us. We not only serve the Department of Air Force, but now the relatively new Space Force. And there's some really interesting research topics that live at the space of those at the edge of those very interesting environments, especially once you get into the austerity of space. And I just want to make clear that I'm very comfortable with answering questions on the fly. I think it'll help, especially at the beginning of the presentation, talking about the nature of the research at AFRL. So if you have any questions, please virtually raise your hand and I'll try to address it. If not, I'll leave enough time for hopefully a very fun Q&A session at the end. So as I described, I'll first be talking a little bit about who AFRL is, who we are, what we do, where we work, how you can engage with us. I think that's probably, if I wanted to get one big thing out of this talk, that would be it. Some engagement after the talk. We always are looking for collaborators, partners, talent, etc. I'll discuss what the Digital Manufacturing Research Team, which actually is only 3 years old at AFRL, very, very new team, which should provide some, I guess, some flexing for PhD students that are working in this space, that there's continuing investment in digital manufacturing. I'll then dive more into what we've contributed in industrial AR, which has mostly, to be frank, has been at NIST since I only joined AFRL 3 months ago and still standing up a team and some environments there. And then, of course, because I'm relatively new to AFRL, a lot of, I'll spend a considerable amount of time, maybe 5 minutes at the end, talking about what we're trying to do looking forward. So first of all, who is AFRL? And there's a lot of words on the slide. Please take this home to yourselves. I'll provide the presentation to everybody. But it's a really large organization, some over 11,000 employees as the primary R&D center for the Department of Air Force and Space Force. And the workforce is a mix of military personnel, government civilians like myself, who make up the primary bulk of the research and the engineers and scientists, and then also contractors, which also play a very important role that I'll explain a little bit. So the total budget of AFRL is significant, $5 billion a year, and that does not take into account salaries of on-base personnel. So it's even bigger or bootstrapped how much capabilities we have in terms of funding internal and external work. To give you a sense, at NIST, this is including personnel at NIST, the total budget of all of NIST, including the Nano Center, materials, engineering, is $1 billion, and that's including salary. So to give you some sense, AFRL has significant more funding. Our locations are kind of all over the US, but including 3 co-sponsored sites outside the US. And as old as the Air Force has been, the AFRL has been there to help. So as I mentioned, a significant number of employees. Most of the scientists and engineers are government civilians, so there's no military service included in that. And the higher degrees are very much valued in this organization, as the grand majority have at least a master's degree, and a third of the scientists and engineers hold a PhD. I also wanted to make it clear that, you know, another important factor is that they try to make sure that there's a considerable less, or we are like a lean organization where most of the management, or I should say the admin folks, are military personnel, where, you know, civilians are more geared towards conducting that research itself. So where are we located? So the headquarters, along with my particular division, is in outside Dayton, Ohio, and if you're not familiar with military bases, they have their own city callouts. So we're located technically in Wright-Patterson Air Force Base, Ohio, which is for anybody that maybe is not on the base, it's just Dayton, Ohio, and a lot of the core research takes place in Dayton, specifically, and, you know, very central to AFRL's mission is materials, advanced materials, not only the creation of new materials or the investigation of new materials, but then also if something goes wrong in space or in flight, for instance, like a fracture that occurs due to some grain boundary in a composite, they bring that component, sometimes a number of those components, to the Air Force Base in Wright-Pat, and different teams will activate work on it to understand what happened. So there is this kind of understanding of how we can improve the flight mission capability of our airmen by understanding what happened, so kind of problem solving, but then also more core research, more akin to academic settings. And because of the really diverse funding and capabilities that we have, that we're very blessed to have in the Air Force, we have some really incredible facilities. And I'm just, you know, still learning about everything that's at our fingertips, not only in Dayton, but across the US. One really cool center, in my mind, or my opinion, is the AMOS Center in Maui, Hawaii, that you see in this top left. Which basically is an observatory and a supercomputing site, image classification, image understanding of observations in space. We also have the only DoD human-rated centrifuge, and this actually sits at Dayton. So this is to basically train up astronauts, but then also you know, fighter pilots to be able to withstand certain Mach. And of course, like even our labs that we have direct ties to, there's a whole lot of autonomous research going on. Automation is one of the key notions of the digital manufacturing research team that I'll mention in a little bit. But if you're ever able to get you know, security clear, it's not necessarily clearance, but a tour of some of the capabilities of Wright-Pat, if you're ever given that opportunity, I highly recommend doing so, because there's just some really, really impressive stuff. You know, I've been blown away just by looking at other people's setups, and maybe that's afforded by the very healthy budget that we are blessed with. So what do we do? So this is a infographic that you should be able to find in the websites that I provide at the end of the presentation. But what this does a pretty good job of explaining how diverse are the research topics that AFRL is addressing. And we address these topics at multiple scales. And what I mean by scales is either in the basic research, applied research, or even technology transfer domain. I'll get into that a little bit more in the upcoming slides. But as you see, there's kind of a particularly heavy focus on what you would expect on flight capability in our munitions, technical competencies, a lot of materials and manufacturing focus that, of course, I'll talk about because that's where I sit, but also very strong influence in what I would consider on the industrial engineering side, a lot of human factors research, and a lot of interesting kind of systems level thinking. So if you can see an eye-popping kind of call out here, even if it's just one term or keyword that you see on the space, you can imagine that there's you know, maybe even hundreds of people that are working in that area. And there's a lot of cross contamination of good work that goes on between these core technical competencies, of which are sometimes even directed in a hierarchical sense through a directorate or a group of people working on a particular problem. So I hope, maybe you see some things that connects with what you're doing in your work. If so, please keep Air Force in mind for some potential collaboration or even career opportunity. So I mentioned that there's kind of this notion of a wide scale of the kinds of work that is conducted at AFRL. And so there is this kind of basic research, new way to, for instance, develop aluminum in space or create refine aluminum in space. That's a real topic, right? And there's some real basic questions that are being driven there, or even some basic propulsion questions. And I would call that more basic. So when you think of manufacturing, at least in the context of AFRL, I would say most of our work sits within what we call the 6.2 investment category, which is applied research, where we use those basic understandings and then implement them to apply that knowledge on a particular domain, whether that be manufacturing, whether that be flight, et cetera. So that's really where the sweet spot, at least where my work and my team's work fits in. But then we also have, which is really interesting because this is quite unique to AFRL compared to some of the other armed services research labs. We also have folks that specifically work on the tech transfer, where they fund external efforts from the industrial base to turn even things that are developed therein within AFRL to practice, to fly, or even to go to space. And what I mean by that being particularly unique to AFRL, let's take our friends at the Naval Research Lab, for instance. They are separate from the Office of Naval Research, ONR, which is basically where your PMs, you might have heard PMs, program managers, sit, that then fund that external work. So they don't sit together explicitly. And I think this kind of sitting together, literally, and sitting in the same meetings, having a clear sense of what each other's goals are, I think provides a very interesting flexibility in our work. So there are many ways to partner with AFRL, and this is just a very high level kind of graphic. You can find more information on the website, which is at the end of the presentation. In fact, you can see it right here at afresearchlab.com. One thing I'll just mention is we do provide internships in different ways. Mostly, I think they have to be a U.S. citizen or at least a permanent resident. But then there's also ways of building up a small business. We're a big funder of small business innovation research grants. And on a personal note, I've had friends back when I was a PhD student that went on with some ideas from their dissertation or something related and actually built a business. They were very strong entrepreneurs. And a lot of that seed funding for their business came from SBIRs. In those cases, it wasn't necessarily Air Force, but it was other DoD services. So that's something to really consider, especially for your PhD candidates that are trying to figure out what to do next. But there's lots of ways of engaging with Air Force. One thing that I'll mention very strongly is we have a very strong partnerships with the Manufacturing USA Institutes, which I'll explain a little bit in the upcoming slides. Okay, so I hope that was helpful, just to give like a broad kind of view of where AFRL sits and where, what we're interested in, which is quite broad, from basic material work all the way to technology delivery on the flight line. Now to like more hone down into what my role is and what our team specifically does. I'll explain it's not that big of a hierarchy, but we sit within the Materials and Manufacturing Directorate, which directly relates or connects or maps to those core technical competencies. Don't ask me why the acronym is RX. I won't be able to give an answer, but it is. I won't use RX, I'll just use Materials and Manufacturing Directorate. And under that, we have a series of divisions, one of which is the Manufacturing Industrial Technology Division, which is where the Digital Manufacturing Research Team lives. And that digital manufacturing research team is an interdisciplinary team across RX, not even necessarily the manufacturing industrial technologies division. We have folks that are experts in automation, robotics, additive manufacturing, material scientists, somebody like myself, who's I would consider myself more computer vision and AR. And we try to address our stated goals, which I'll get into now or in a little bit. So just like the grand vision of AFRL, RXM is no different in that we really fit the gamut of from these what I would call the applied research all the way up to full technology insertion into the flight line. And one thing I wanted to pay particular attention to is our interaction with Manufacturing USA. So if you're an aspiring researcher, a PhD student that maybe is going to look at a career in academia or even a career in some research institute or even in industry, I would really take a close look at Manufacturing USA if you don't know much about it. So there are a series of institutes that were funded during the Obama administration and throughout, from then to focus on particular manufacturing domains. They have stuff in flexible electronics. They have a center specifically focused on biomanufacturing and others. So the three main centers that Air Force has a heavy hand in and interacts with quite significantly is the Advanced Robotics for Manufacturing Institute, or ARM, that sits in Pittsburgh. We actually, our team, or my colleague just released a call through ARM for work related to Future Factory. And we also interact with MXD, which is the Digital Manufacturing Institute located, I believe, in Chicago. And the third one that we really have a heavy role in is America Makes, which is the additive manufacturing, and I believe that's in Kentucky. So again, if you're focused on any of those areas, really check out what Manufacturing USA is calling for, because I think that could provide either motivation or a center point for some research moving forward. So one of the key acronyms, and I think this is my last kind of overview slide of AFRL, but I think it's really helpful to understand where we sit and how we do work. One of the key acronyms that if you're going to learn any acronym, I think TRL is most important. And TRL stands for Technology Readiness Level. It's a way that the DoD is able to describe at what stage a particular technology or research sits in. And there's also other ways of describing it. Some people use manufacturing readiness level, which more or less maps to these same kinds of trends. And I want to be pretty clear about where our digital manufacturing research team sits. So we sit, or our goal is to address problems between MRL 2 to 4, which could map to TRL 2 to 4, which basically we look at new novel techniques to apply basic findings and then develop them to proving feasibility. So most of my work at NIST, for instance, that I'll share, will be kind of at this edge of TRL 3 to TRL 4. So you might be looking at it and thinking, it's applied, very applied, and we can get into how you can position your work to fit within this framework. And again, the folks that I was talking about, these program managers that then bring some of the work that has been realized through the digital manufacturing research team, sit within this ManTech program that move from TRL 4, from proof of feasibility, so they know that it's worth funding, and then they fund usually external partners to bring it to a level of at-scale demonstration, which kind of sits around TRL 7. So that's all I wanted to really talk about that. Now I'll get into what we're trying to do in the digital manufacturing research team. So we kind of live by this mantra that my colleagues came up with a couple of years back, this concept of teaching tools to be teammates. And tools is used very loosely, could be a virtual tool, could be a physical tool. And within that mantra, we have these 3 lanes that we want to address. One of which is how we can create new modes of human-machine interactions. And that could be on the interface level, whether you're looking at mixed reality applications, which I'll talk about in next. It could be about abstracting some knowledge from expertise. And you see this example of a carpenter that's working with his hands. How do we translate that to have the same kind of tactile feel on the material workpiece? If you're using a large robot, a lot can go wrong. If you've seen some of those funny YouTube clips of when robots go wrong. And then in an ideal world, kind of get to the level where we can sense and monitor on a machine as well as, let's say, a gymnast or a great athlete. And to support those kinds of modes of interactions, of course, we're looking a lot at machine intelligence or AI, machine learning. This could be lots of kinds of data fusion techniques for autonomy. We do a lot of that kind of work. Improving agile decision and control at the machine level. And here's a kind of an old school picture of what HMIs still look like now. Like what would be the next capable kind of platform to interact with, let's say, a machining center. And of course, be able to derive value from those lessons learned into some way to share that information within the team and beyond. So we're looking at things like Google Cloud and do a lot of work in how we can label data appropriately and repurpose data for different applications. And at the heart of all this is kind of this notion of how we can trust how human and machine agents are interacting with one another. So we do have some work that I think was just presented this week at MRS, which is one of the foremost materials conferences on using explainable AI to understand autonomous material experimentation. So the basic idea here is how we can move away from a black box approach, even though that many of those black box, not necessarily move away from black box, but black box algorithms like deep learning provide a whole lot of great tools for us, but how we can understand the biases within that black box to open it up to the human to make sure and validate, to expand the trust in what actually is happening. So from those kind of central points, we are working on these more or less enduring research questions. And this is more of a summary of what I just mentioned. How do we capture and deploy human expertise to make them more autonomous or semi-autonomous sometimes? How do we create a shared environment, describe it in a computer interpretable way for human-machine teaming and communication? And then how do we interface to expand machine intelligence? There's this GIF of one of my colleagues, Anicia, who is working with a robotic arm to look at how best to profile a spray pattern for a very specific mechanical test. It's just an example. So we're studying whether we should have humans directly interfacing with the arm, if the arm should be autonomous, or if we should interact it with some virtual simulation like a VR headset. And then of course, if you have a very well-controlled or almost overly controlled, over-constrained robotic environment, we have to look at how we can rapidly retask it and kind of unconstrain it, or at least relax the constraints for repurposing use. That's a very important concept. And then I already mentioned about this concept of human-machine understanding and trust. Okay, so I hope that provided a more or less kind of an overarching vision for what the digital manufacturing team is trying to do. And we all kind of have our own ideas on how we can influence those questions. And one of those from my end is, this is continuing work from NIST, is how we can make more, let's say, interoperable, maintainable, and reproducible AR installations for manufacturing. And to do so, what's really important is to create an AR-capable digital thread. Okay, so I want to explain what I mean by digital thread first. So this is under the context of these kind of buzzwords that many of you might have heard, the idea of Industry 4.0, or the fourth industrial revolution. It goes beyond just using computers for autonomy. That was kind of the third industrial revolution back in 80s, 90s. Now what we're doing is, since there's this ubiquity of digitalization of basically everything can be connected over the web through this concept of Internet of Things, there's a lot more potential for gaining knowledge of similar systems, or even systems that are not intuitively similar. And most of these concepts are kind of built in the context of the intersection between advanced manufacturing services, and I show a few examples of being able to print on electronics, additive manufacturing, where you can create really fancy geometries without the traditional constraints of subtractive machining, robotics, and flexible materials, along with the state-of-the-art digital infrastructure, which is being exploited way beyond manufacturing. And those include image classification, recognition, computer vision procedures, leveraging the cloud for basically offloading computational effort for whatever you need. Mixed reality interfaces, if they're worthwhile. A lot of times people use them even though they're not worthwhile, but I'll show you, what we're doing there. And then, of course, this whole idea of graphing or networking information in a more intelligent but flexible way, so that we can conduct reasoning on how different knowledge relates to one another. Okay, so a lot of people have been doing all kinds of work in this space. And the reason why I call it smart manufacturing, or that's at the top, there's a bit of a tussle between the US side and the Europe side, where I don't think, if you look at any government, at least from the president or something like that, report, they won't really call it Industry 4.0, they'll call it smart manufacturing. That's just because Industry 4.0 was technically invented, the term itself, by the German government. Okay, so why is this so complex, and why is this so difficult to realize this digital thread? So if you open up any kind of undergrad product development textbook or mechanical design textbook, you'll see this top more or less these stages from right to left, where you have to go through these stages that are detailed, very well at this point. How you produce drawings for managing the production of a part, and then once you deploy that deploy those plans into actual production, there then becomes this kind of material flow that is, is quite forward-feeding, from extracting material all the way through its eventual disposal. But what's interesting in this figure that we created a few years ago is how complex the information flow could be if all of these, and how they can back inform upstream processes if the digital thread was connected. You can imagine a situation where, let's just say an airplane, right? People talk about the idea of digital twin a lot. An airplane is in flight, and you want to know right away what's happening on the turbine blades in the particular engine. And if you had this forward-back kind of understanding of what's going on at that time, that could already change the next evolution of a new product. Or, of course, it could inform how you're going to reuse some component or remanufacture it. So there's a lot here, and the goal of the digital thread, in my mind, is to basically realize all of the blue lines in this figure. And there's been lots of standards activities related to different elements associated with the figure in the last slide. There's been work on how we can read out information from machines in more, I would say, structured ways, like time-stamped manner, for instance, in a standard way. MT Connect is a big effort, and MT Connect Institute. Also, OPC has been around for a long time, that looks at how we can message between machines in a standard way. But then there's also a lot of work on how we can just simply store information that's coming off the manufacturing floor. For instance, DMSC came out, and I'll talk about QIF a little bit, which I think is a great standard, that basically provides a platform, a standard platform for labeling inspection data. And inspection is a very, very important thing in the Air Force. But the challenge really is, because all of these different standards, these are standards communities, but there's lots of standards under them. The challenge is really harmonizing across them. because they've all been created with their own goals and intent in mind, which is fine. But to really realize this connected digital thread to solve problems across life cycle stages, we need to be able to basically have the data formats themselves to be interoperable with one another, to really have strong insights. Let's say you just inspect a hole, for instance, in a plate. You need to know right away who designed that hole, meaning like what company designed that hole, and how we can address that problem if something comes back in red. Okay, so that was to provide a context of what we're talking about in digital thread in Industry 4.0. So one of the elements of Industry 4.0 is this notion of interfaces, how we can use these visualization interfaces to have more contextual awareness of what's going on in the design and manufacturing stages. And broadly, we can think about them in across a spectrum, but in 3 different buckets. There's work in augmented reality, which is, in my opinion, basically just superimposing a digital object onto the real world, some site of the real world through a camera. In this case, you see this lady with a tablet and showing some digital object in reference to physical objects on the table. You have this notion of virtual reality where you're fully ensconced in a virtual simulation or virtual world, and there is no direct connection to the real world, meaning that you're totally immersed in that world. And then there's this notion of mixed reality, where I guess the most prominent example of this is Microsoft HoloLens, where the notion here is, in my mind, it's kind of like an augmented version of augmented reality, where you now have this notion of interacting in the real world, and that changes how you're superimposing digital objects. So there's some kinds of interaction that could be with your hands, it could be even with where you look, tracking your eyes, etc. But we should think about this spectrum as exactly that, as a spectrum. So the work that I've really been focusing on is on AR. And the reason I've been focusing so heavily on AR is simply that's what's being used most on the floor in manufacturing. There's lots of reports to support this, but it's the easiest to deploy at scale, and there's less training involved than anything else. It's quite natural and people understand it. Okay, so what's the problem with AR? We basically have AR capable devices in all of our pockets. If you have a smartphone, you can play Pokemon Go as an example, and you can have a grand old time. But the main issue, right, is how do we harden these technologies in industrial sense? And we can think about this problem in kind of 3 categories, and I'm just showing 2 for now right here. Most of the work related to industrial augmented reality has been around this notion of how do we capture the real world and present a computer interpretable representation of it, a 3D representation, so that we can superimpose something on that real world. The other components of work have been on, once you understand or can model the real world in a digital sense of it, how do we then render those notions on top of the real world and present it? But what's really challenging here and requires a lot of person hours is how do you connect the domain specific models, whether they be devices, people, spaces, etc., that relate the real world to this presentation. And basically this blue box is all the Industry 4.0 standards that we already mentioned. So the goal of the work that I'll just show you now is on basically how do we connect these dotted lines in a more easy, scalable way. Okay, so really quickly, there's been a lot of AR standards. There's a great paper. At this point, it's a bit old. I think it's about 4 years old, that lays out all the different standard organizations around AR. Many of them are aware of the Industry 4.0 problems, and there's a whole lot of work around it. And I won't go that much into it unless there are some questions at the end. But please feel free to check out this paper from EPRI, from EPRI. Okay, so before I show some demonstrations, I would like to acknowledge the great people at NIST and the folks that worked on this project, whether they be associates, and it was really a pleasure working with them. So the first is a very explicit example of how we connect kind of the industry 4.0 harmonization design inspection data within AR. So this will just be a really quick background, and I feel free to check out some of the links that I shared here on what kind of standards we're using. If you've ever used a CAD environment, you say file, save as, or export as, you'll see STEP in there, STP. STP is a huge standard. It's a monster standard, but it governs the way in which geometry and manufacturing information are expressed between life cycle stages, in short. But there's also standards around how annotations are displayed on a 2D screen, and those are in ASME Y14. These annotations I'll be describing as PMI, product manufacturing information. This PMI could be how to make something, how many to make, but it's mostly about the geometric dimensioning and tolerancing of different features around a part. The reason why we need a neutral format is basically to trade information across different platforms without loss of information. So there's a considerable effort at NIST that I know that some of you are aware of, where we test, or they've tested, how well different platforms like CATIA and X, et cetera, conform to the STEP standard. And in an ideal world, importing a STEP file would maintain everything exactly the same. Okay, another standard that we spend a lot of time on is the quality information framework. And this is a really large XML schema that basically delivers labeled data for any inspection results, but then you can also represent plans on how to inspect a part. So the problem with connecting these two standards is that though they share a lot of basic information between STEP and QIF, for instance, like geometry, topology, GD&T, they are represented very differently. So they're represented, QIF is represented as more or less a flat file in XML, while STEP is an object-oriented language in Express. So the idea here was, how can we create them or lift them up to knowledge graphs to be able to connect them and reason on top of them, so that rather than an engineer look at a spreadsheet and try to match this data manually, we're able to reason on it naturally with a computerable interpretable representation. I realized I went a little bit too far in some of the earlier slides, so kind of speeding through this, apologies. So what we did is we developed tools and methods to basically ontologize the data representations. So, and you can find these online at full resource, full source code at the US NIST Gov GitHub. So first of all, I guess what is the real meat of this work was ontologizing STEP. Actually, we just came out with a technical brief. This is like a week ago, that you can actually really get this in detail of how this was done. But basically, you run it through our translator and you get an OWL representation of a STEP file. And we used an existing available online to translate XSD to OWL. And in doing so, what we're able to do is, rather than use mapping tables, this is actually really this is actually very common in industry to map between different data types in this kind of tabular way. We're able to formally express it in a query language, so that ideally this, and I guess theoretically, this query would never be broken based off of whatever data we have coming in, so that we can instantly have a sense of how things are connected to one another. And we tested this in the case that I shared of this assembly, and we're able to quickly determine which inspection criteria failed on specific features. Okay, so what we did then is we used that same mapping technique and then derived a pipeline to then show this in AR. And the reason why this is so important is that those dotted lines that I showed you before, all this had been done manually beforehand. And when you look at these, I think there's, when you look at these step files, they're separated into views, where the views of the geometry itself are expressed and these views of these annotations are expressed. So we leverage the concept of views to express the tessellated geometry that can be placed onto an AR scene using X3D, which is, I guess, amenable to AR. Of course, it would be better if we were used to data representation, which is a little bit newer and better at runtime, something like GLTF. But we're still looking at how we can do that better. So this source code is available. I think the link is on the next slide. But the general pipeline is we read in an insta file a step, we spin it through some, again, publicly available executables, and we create an annotated X3D file, which maintains the spatial orientation of these annotations against the original geometry of step. So as far as we know, there's a commercial effort that does this, but this is the first open source development project that presents, or I guess, conforms to the standards, where you're actually looking at the standard spatial representation of this information in AR. And you can see that you can just for demonstration's sake, we then put this into a Unity application, and we threw a tracker toolkit on it using Viforia, which has its own problems. If you want to ask me about it, you can. And it works quite well. And in the left figure, or I'm sorry, the left video, what you see is us actually querying through the different QIF-based inspection results. And we just did a simple filter: green showing which ones passed, yellow which are a little bit murky, which fail on different measurements, and red, which is definitely a problem for that particular feature. This DOI, I just put this in today because today this was posted as an accepted manuscript, and you can check out all the nitty-gritty information on how we did this. Okay, so another example of how we can merge standards for AR manufacturing is another thing about how we represent spaces in manufacturing. So there's this standard called the Open Geospatial Consortium Indoor GML. And Indoor GML is a pretty advanced standard that basically presents a graph-based representation of how you move in spaces, in indoor spaces. And the idea here, and this was just a simple project to demonstrate why it's important to merge standards from the XR world, the AR world, and the Industry 4.0 world. And another standard that's important here is MT Connect. Really, I mentioned it really quickly, which basically provides a labeled representation. I'm sorry, yeah, a timestamp representation of what's coming off the controller in a standard way. And the idea here, or the objective here, was to basically model a workshop. In this case, we used the NIST workshop, actual machine shop, to model the workshop in Indoor GML, and then relate that to live streaming data coming off the machines. And the idea of this was to not make some really awesome VR AR scene, which we could do, and we did do a little bit. It was more to show how important it is to have these two standards kind of interplay with one another, so that you can quickly generate different views of what's going on. So in this case, what you see is yellow machines are offline, or not ready, I guess is a better word. Red are in use, and green are available. So really quickly, you get a quick sense of what's going on in this Unity scene. And a student used the same kind of notion to create this really quick tablet-based application. I'm not suggesting this is AR VR, to basically find the shortest path between going from one station to another. And I want to be clear to explain that the waypoints and transitions, or paths between these different machines, is all modeled within a standard format called Indoor GML. So this scene, I'm not talking about the menu options and everything like that, but the scene itself is already created. So all it has to do is just load it up into Unity and parse it, which we developed, and everything is there for your taking. There are some indoor GML parsers available online. They're just a bit buggy, but you can see that he's able to access some data about each machine, access manuals about each machine, and give a sense of how the maintainer should go from one machine to another. There are some takeaways that I would invite you to check out in the paper on how I guess the gaps between merging one data model with another that are not exactly, were not thought of from the beginning of how you can bleed over into a domain of manufacturing. So we had to take some interesting design liberties, for instance, saying that a tool is like a piece of furniture that you can move around, but a machine is like a column in a building that cannot be moved. So anyways, you can check out more of the paper. Lastly, I just want to go into some ongoing work and some future directions. I think I have some time here left, and explain some additional things that we're really looking at with some contractor primes, and how we can expedite some of the processes of developing AR systems. So if you're a AR developer, you have some idea of kind of creating augmented reality applications or even VR applications, you know that rigging is a really important notion. And the reason why it's so important is it expedites the way we produce animations of characters. So this has been a long-going, well-known study field. There's even papers that can automatically segment shapes to create rigs on the fly of 3D models, or I'm sorry, of humanoids and other kinds of animal structures and amorphous structures, everything like that. But the notion here is, if skeletal animations have basically lessened the cost of movie production and gaming production and everything like that, can we use the same notion of separating how models move with respect to one another, like the skeleton, against the model itself, so that we can create more diversity in industrial animations? And when I mean industrial animations, I'm talking about assembly of products. So this is a notion that we're exploring, so that we can build libraries of animations to quicken the pace of development. And the reason why this is so important is, let's say you have an animation that describes how to put together a circuit board. If something breaks upstream, meaning like you need a design change of where a transistor goes, you basically need to invite all the other AR developers, the artists, the industrial designers back in to retool the animations in something like Blender or 3ds Max. So the notion here is, can we create more of a flexible animation definition so that if there's something that changes on the assembly line, you basically lessen the cost of redevelopment. Oh, and oh, it's not. Okay, so let's see, it's not playing really well. So we had so I just want to be clear that this was a 10-week internship. So, this is a bit messy, but I think it just crashed. Okay, I'm sorry. Oops. Sorry about that. I think I'll be able to share quickly here. Sorry about that. Okay. All right. Okay, I think you can see the application. Let me just skip to. Okay, so I'll just skip that slide if that sounds like a no-no slide. But basically, that was showing that we do have an example of a collada, which is a data format for animations and other kinds of virtual scenes, where the model itself, in that case, we were showing a screw being screwed into a nut, is separated from the motion. And to decouple those two, I think is really a significant, even though it's very it's kind of like on the development side, very applied work. I believe that could be a useful way of strengthening and maintaining industrial animations. So sorry about that that little drop there. So just really briefly, I just posted some 4 general directions for future research and opportunities. And if any of these strike your interest, feel free to email me and let me know, or we can ask questions about it. So first, this is a project that I've been trying to get up and running with several industrial partners, and I think we're getting closer and closer. But there's always been this really huge problem of determining what the right mix of asset localization for tracking, parts for pose estimation in factory floors. Not only factory floors, but really austere environments where there's a lot of clutter, lighting challenges, telecommunication barriers, where there are huge metal boxes. Asset symmetry is a really big one. If you have a gear where every pose of it looks the same, how can you know which feature you're particularly interested in? So there's some work that is now being dug up by me and some collaborators on how we can inform the right tech mix and how we can build redundancy in AR systems for tracking. So if there's an occlusion, you can switch modes directly to a radio frequency kind of mode like ultra wideband or Bluetooth. While if there's, let's say, huge metal boxes in the way, we can switch to some computer vision technique, whether it be model-based or SLAM. So that's something that we're really thinking about. I already talked a lot about this concept of making more maintainable, reproducible, and flexible animations in AR. I think there's a lot here. So I just had a really nice conversation with the developer of the, and I know this might be a little jargony, but the ABC dataset, Daniele Pinozo, I think his name is, in Colombia, who's really, they've done some great work in releasing a really large data set of models. They're interested in this problem. How can we learn what the animations are by some segmentation of an assembly? These are all things that I think are definitely on the table to quicken the delivery of these scenes. Like always, we're always interested in how we can leverage Industry 4.0 technologies in space, and also in environments where the communication barriers are immense. And for instance, in Department of Defense depots, which are in-field maintenance service centers. There's a buzzword going around that really hasn't reached, I would argue has not really reached the industrial engineering and mechanical engineering world, called OSAM, which stands for on-orbit servicing, assembly, and manufacturing. A lot of that has been written about in Aero conferences, but there's a lot to, I think, a lot of opportunities for understanding how, for instance, robotics, automation work on satellites, how we can reuse space debris. There's a lot of cool directions there. And lastly, like always, we're really still, this is going to be a key notion of our work, is to continue our work towards human-robot interaction and teaming, whether it be in field with semi or fully automated guided vehicles, like you see this guy right here, or using different kinds of extended reality applications and how we communicate with robots. This is actually a NIST picture of Shelley Bacci, who works in the HRI lab at NIST, a former collaborator of mine. So with that, please feel free to check out what else is going on. AFRL, I would say, is a much more open, kind of like in what we have been doing, as opposed to maybe some of the other armed services labs. That's one of the reasons why I think management has been so accepting of moving to a Google platform called afresearchlab.com. So you can find a whole lot of what's going on there, as opposed to the kind of like the old school traditional, more secure mill website. So you can find a whole lot of information of what's been going on in this website. And with that, I'd like to take any questions. And I apologize, I meant to finish a few minutes earlier than that. Thank you.
Thanks, Bill.